Hi, how is it going? Some of you might know that building your own robot is an exciting project. One of the biggest challenges in robotics is figuring out how to make the robot's hand go exactly where you want it to. That is exactly what inverse kinematics, IK, does. If you use forward kinematics, you are guessing or saying, if I turn the shoulder motor 10 degrees and the elbow motor 20 degrees, where will the hand end up? Inverse kinematics flips that around. It lets you say that I want the hand to grab an object at these exact coordinates, x, y. Now tell me what angles the motors need to be. Let's imagine that your robot arm lying flat on a table, and here is our vocabulary. L1 is your upper arm, link 1. L2 is your forearm, link 2. Theta 1 is the angle of your shoulder joint. Theta 2 is the angle of your elbow joint. And finally, XY is the target spot that you want the fingertips to touch. First, we need to find out how much the elbow needs to bend. To do this, we imagine a triangle formed by your upper arm, your forearm, and an imaginary straight line drawn from your shoulder directly to the target. The equation for the elbow is cosine theta. 2 equals x squared plus y squared minus L1 squared minus L2 squared divided by 2 times L1 times L2. Some people might ask, why are we using this? X squared plus y squared. This is the Pythagorean theorem. It finds the squared length of that imaginary straight line from your shoulder, 0, 0, to the target, x, y. The whole formula. This is called the law of cosines. It's a geometry rule that finds an unknown angle of a triangle if we know the lengths of all three sides, which we do L1, L2, and the imaginary line to the target. Once you calculate that big fraction, let's call the answer D. To get the actual angle in degrees, you use the inverse cosine button on your calculator, often written as arcos or cos to the power of -1. Theta 2 equals arcos of D. Now that we know how much the elbow is bent, we can figure out how much the whole arm needs to tilt from the shoulder to aim exactly at the target. The equation for the shoulder, theta 1 equals arctan, divided by x minus arctan L 2 times, sine theta, 2 over L, 1 plus L, 2 times cosine theta 2. And here is a quick extra note. If you program this later, you will use a function called atan2 instead of regular arctan, because it handles positive and negative directions perfectly. Now let's explain why are we using this formula equation. Firstly, arctan yx. This finds the angle of that imaginary straight line aiming straight from your shoulder to the target. Secondly, because your elbow is bent, your hand isn't perfectly lined up with that imaginary straight line. This second piece calculates exactly how much we need to correct the shoulder angle to make up for the bent elbow. We use standard trigonometry, sine and cosine, to figure out the height and width of the bent arm so we can find that correction angle.
Let's walk through an example. Let's say that you are building a robot with link 1, L1 equals 10 centimeters, link 2, L2 equals 10 centimeters. You want the robot to touch a target on the table at coordinates x equals 10 centimeters, y equals 10 centimeters. Now, let's try to find the angles. Our first step is to calculate the elbow with the law of cosine formula that we have previously talked about. If we plug the numbers into the elbow equation, we get cosine theta 2 equals 10 squared plus 10 squared minus 10 squared minus 10 squared over 2 times 10 times 10. This gives us cosine theta 2 equals 100 plus 100 minus 100 minus 100 divided by 200, which is 0 over 200 equals 0. Now, what angle gives a cosine of 0? Well, theta 2 equals arcos of 0 equals 90 degrees. Good, this is telling us that the elbow needs to be bent at exactly a 90-degree right angle. And we have finished step 1. Step 2 is to calculate the shoulder, theta 1. Now plug everything into the shoulder formula, knowing theta 2 equals 90 degrees, which is theta 1 equals arctan 10 over 10 minus arctan 10 times, so 90 degrees over 10 plus 10 times cosine 90 degrees. Let's simplify it. If you check a calculator, you'll see sine of 90 degrees equals 1 and cosine of 90 degrees equals 0. Theta 1 equals arctangent of 1 minus arctangent of 10 times by 1 over 10 plus 10 times by 0. Theta 1 equals arctangent of 1 minus arctan 10 over 10. Theta 1 equals arctan 1 minus arctan 1 theta. 1 equals 45 degrees minus 45 degrees equals 0 degrees. So to touch the target exactly at x equals 10, y equals 10, your robot needs to set its shoulder motor to 0 degrees, pointing straight sideways along the x-axis. and bend its elbow motor to 90 degrees, pointing straight up. If you draw that out on a piece of graph paper, a 10 centimeter arm going right with a second 10 centimeter arm pointing straight up from it, the fingertip lands exactly on 10, 10. That's basically all for this video. If inverse kinematics felt intimidating at first with all the trigonometric equations, don't worry. That is completely normal. Just sketch a 2 degrees of freedom robotic arm and label them with various lengths and XY coordinates to practice. The secret to mastering robotics is realizing that complex robot movements are just simple geometry under the hood. By breaking down your robot's arm into basic triangles, you turned a hard problem into 2 math equations that your microcontroller can run in milliseconds. Once you upload this code to your robot, you move from forward kinematics, guessing motor angles, to true automation, telling your robot where to go and letting it figure out how to get there. In the next video, we are taking our arm off the flat 2D table and launching into 3D space. We'll add a third motor at the base to create a 3 degrees of freedom robotic arm. You'll see how a clever 2D projection trick lets us reuse all the 2D DOF math we wrote today so you can command your robot in 3D coordinates, X, Y, Z. See you in the next build.